This is the video to help you analyze the data from the Hooke's Law experiment. Here I'm showing a picture of the spring scale that was calibrated during the experiment. What we're going to do is to identify for each load, we will identify the extension. So I'm going to make a table. This is the load in newtons: 0, 0.5, 1.0, 1.5, 2.0, 2.5, and 3. And then for each loading, I am going to determine the total extension of the spring in centimeters. At 0 loading, we have 0 extension, shown by this point, because we've lined up the ruler, the 0 of the ruler, with the 0 newtons. At 0.5, we, right here, it's at 1.2 centimeters. At 1, it's at 2.6. At 1.5 newtons, I'm getting 3.7. At 2 newtons, I'm at 4.9. At 2.5, I'm at 6.2. And at 3, I am at 7.5 centimeters. I'm now going to plot these data points, plotting the load on the y-axis and the extension on the x-axis. To plot my graph, I will first look at the range of values for each axis. So for the y-axis will range from 0 to 3. So if I were to sketch where I want my y-axis to go, let me count up how many squares there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 squares, and I'd like to go up to, those 20 squares to represent a total load of 3 newtons. So in such case, it seems probably easiest to use 5 squares to represent 1 newton, in which case my scale will go, if I call this here my 0, this will be my 1, this will be 2, and this will be 3. So each square will represent 0.2 of a newton. So I will label my axis load in newtons. For the x-axis must go from 0 to 7.5. So let me count how many squares I have on the x-axis. I have 27. So, and I want to go up to 7.5. Seems that if that's 27, we could go up to 30 over here. So if we use 4 squares for each centimeter, let's see if that works. 1, 2, 3, 4, 5, 6, 7, and at the extreme here will be the 7.5. So going right up to the edge of the graph. That's probably not recommended. We maybe want to go back and shift the graph across. But I'll stick with that for now. Now we've got to plot the data points. So I'll switch to red here. We've got one data point at 0, 0. At 0.5 newtons load, the extension is 1.2. So each one of these squares here is a quarter of a centimeter. It's worth 0.25. So it's going to be just over here. There we go. The next one is at 1 Newton. It's going to be 2.6. So there's 2.5. 2.6 will be somewhere in the middle here. .5 Newton load, which is over here, and that will be at 3.7. So I know 3.75 is here, so it's going to be around here. For 2 Newton load, the extension is 4.9, so it's almost 5. For 2.5 newtons, the answer is, the extension is 6.2. There's 6, so 6.2 should be around here. And for 3 newtons, we have an extension of 7.5, which goes pretty much off the edge of the graph there. So the next step is to draw a best fit line. So there's my best fit line, and we need to calculate a couple of quantities. The first quantity we want to calculate is called the spring constant. The spring constant is equal to the gradient of the line that we have just drawn. What is the gradient? The gradient is equal to the slope of this line. If we pick any triangle, the ratio of this side here, which is called the rise, divided by this side, which is called the run, that ratio will be the same irrespective of the size of the triangle. So it's best to choose a triangle where it's easy to determine the rise and the run. I think the best triangle is the one that covers all the data points, like so. I'm just sketching the triangle. We can see the rise here is 3 newtons, and the run is 7.5. So our spring constant, which is typically given the symbol K, is going to equal 3 newtons divided by 7.5 centimeters. And that is equal to 3 divided by 7.5. That's equal to 0.4 newtons per centimeter. The other quantity that we want to calculate is called the compliance. The compliance is the reciprocal, meaning 1 over the spring constant. And that quantity is going to equal, just looking it up on my calculator, 2.5, and the units will be reversed from the units for the spring constant, so it's going to be centimeters per newton. And that's how you calculate the spring constant and the compliance of the spring from the load extension data. I realized that what I've forgotten to do was to label the x-axis. So let me do that now. The x-axis is the extension of the spring measured in centimeters. And that completes our graph.